mechanisms. So this is just trying to help you understand like how to draw arrows, how to push electrons, how to draw mechanisms. Okay. So if you don't understand the HOMO and LUMO, review that. Draw the energy diagram. You'll be able to know by doing that. All right. So this one right here, we know it's a positively charged ion, so that has to be negative, making that our base. So the non-bonding electrons on nitrogen are going to grab hydrogen, taking the electrons from this bond in the HS sigma star bond off into the sulfur. You have NH plus S. Alright, this one, it's meant to kind of trick you a little bit. It's saying that the carbon right here is negatively charged. So that would be your base instead of these electrons, because this has a full-on blown charge on carbon, which is very unstable, very strong base. Yeah.
See what happened to the lithium?
Huh?
Or the Li?
It's lithium. It's an ion, so it's just associating with it.
Okay.
It's actually not bonded.
So we don't have to draw it.
No. That's just like, he might give you something like that, and you have to understand that that literally means that this carbon is like this, and the lithium is right next to it.
Okay.
Does that make sense? So this, we'll go and grab the hydrogen right here, taking off the electrons right here, sorry for the small, into the nitrogen, creating a full bond right here, but then it leaves the nitrogen deficient. But it's balanced by the lithium ion in solution. Okay.
I can do the second problem.
Yeah, sure. We're almost done. And then the last one right here, I'm going to draw it. What is our base?
I just have a question. On the nitrogen of D, why do you use the rest of the bond?
With the lone pairs?
Or the rest of the carbon?
Rest of the carbon. Oh, sorry.
Oh, yeah.
Yes, that's how it goes. Thank you. What is the base in this one? This one or this one? This one? Yeah. So this is not methane, almost methane. And because it has a negative charge, it will take this hydrogen before this lone pair can even attack. Look at this sigma, look at the non-bonding electrons here is the HOMO, and the NH sigma star is what would be your LUMO. Okay? Alright. And then in the problem I told you to write down relevant pKa's, and if you know the pKa's, then put them on the reactants and the products by knowing that the stabler your conjugate base is, the more likely your reaction will happen. Okay, so that's
Is it always the one that's being, or so the one that's attacking is your HOMO, and the one that's being attacked is your LUMO?
exactly. Yeah, the HOMO is always attacking the LUMO. It's always filling in the antibonding orbital, breaking a bond, or creating a bond.
So he wouldn't expect you to write out the full electron, whatever it's called.
The energy diagram?
Yes.
He wouldn't, but you need to understand the energy diagram to know what one is going to attack which one. pKa's also come into effect as well. He would give you relevant pKa's so you can solve the problem. Does that make sense?
How does this go down?
Huh?
How does this go down?
This?
No, the projector.
Oh, the projector? I don't know. I've always wondered that. That's a good question. Does anyone know how the projector comes down? What is that? Ah, no.
Well, if you can't do it, you can always put the blackboard up.
Sure. Yeah. Should I just erase this? Are you guys okay if I erase this?
Or you can put the empty one up.
They're all filled. Yeah.
I think that's viewable though,
Can you
right
see it
there.
okay?
What?
The black screen.
No, that doesn't do anything.
It's a good idea, though. I don't know. I've never done it. Never tried. I'm like nervous to press buttons up here because some of them are like hooked up to gas and stuff. I'm like, damn, I can't touch it. I can just erase this. It's not a big deal. Yeah, I can.
That makes it worse.
It makes it worse. I do have them written on the board.
I'll just do it like this. Maybe we could just dim the lights in the front a little bit.
Getting there. Close.
Let's just leave it there. That's good enough. So I just want to pull this up because I'm screen recording this right now for you guys later on. Name the following molecule and show the Newman projection. Draw the three lowest energy conformations looking down the carbon-3, carbon-4 bond. Circle the lowest in energy and relevant pKa's will be on the board. So for this one, you notice that when we have to write down the carbon-3, carbon-4 bond, that's where we have to name it first. So first thing we do here, we identify our functional groups. We've got a chloro group and we've got alkane. That's the only thing we have right there. And then the next thing we do is count the longest chain within the entire molecule. And you see right there, that's only 5. Now there are a couple different ways we can name this. We could go 1, 2, 3, 4, 5. So if we counted that way, it would be 1, 2, 3 chloro, 4 methyl. But that's not the way we want to count. Why is that? We want to give all the groups the lowest number possible. So instead, we want to count from the opposite direction. 1, 2, and let's erase this 4, 3, 4, 5. So this methyl group is now taking on a 2 group, so that's 2 methyl, and then chloro is on carbon number 3, -3 chloro, pentane. But don't forget that we have to follow alphabetical order in order to, or when it comes before the parent chain, which is pentane, it has to go in alphabetical order. So the whole order of this, let's erase this. So the correct order for this is going to be 3 chloro, -2 methyl, and pentane. Make sense? And now, now that we've identified carbons 3 and carbon 4, now we can look down that particular bond to draw our Newman projection. So what's carbon 3 and what's carbon 4 in this case? Here's carbon 3 and here's carbon 4. So if I'm standing right here and Mariana is standing on the other end, we look from where I am, not where from Mariana is. So the first thing to do really is to identify what groups are coming off of the carbon atom. And for this one, so looking down at carbon 3, we've got this group right here, and we've got this chloro group, and don't forget we have this cute little hydrogen sticking up somewhere. I'm going to draw it as going back into the page. And then this carbon over here does have a methyl group attached to it, but it also has the 2 hydrogens as well. Yeah?
As part of the Newman projection, you have to draw the hydrogen.
You wouldn't have to draw on the molecule itself. I'm just drawing that to help to make sure we include all the groups. But you do have to include it on the Newman projection. So doing that, let's pull up ChemDraw. So it looks like a pretty little picture. So notice that with this chlorine and this hydrogen down here, they're kind of facing away from each other, right? One's going down, the other's going left. Let's see, where is my... There we go. So for this one in the middle, or this carbon in the front, we've got chlorine coming out there. Now let's get the periodic table. Chlorine, where's chlorine? So it could go straight down, so let me just finish drawing it out here really quick, and then you'll see what I'm talking about. Let's go back to that. That's not a good drawing. And then back here, I don't really want to draw it out too much. We've got a, whoops, no. And back there, we've got the isobutyl group. So we could draw it like this, but if we rotate it around about 60 degrees or so, we could get it to point down. So really it doesn't matter so much when you're first projecting it out. So we could draw this down and then pull this up. So that way the chlorine, whoops. So that way the chlorine's facing down, and then the hydrogen, we know it has to come up. And then the isobutyl group, or that group on the end, has to come out like this. So both of them are equivalent, not in terms of energy, but in terms of them being on the same carbons. They're the same. We're just showing it rotating a tiny little bit. Does that make sense? So that, this carbon right here in the middle, with the three things poking out from it, that's carbon 2. This sphere in the back is carbon 3 is the one in the middle, and the sphere in the back is carbon 4. Those two are just naturally implied within the equation. Within the Newman projection. Everything else we have to show explicitly. So now looking at this, we've got the two hydrogens coming up. So I'll draw over here first for simplicity's sake. So we know that the hydrogens are coming out from each other at the top. And then the methyl group, the methyl group, which we have right here, is coming down at the bottom. Then we've got hydrogen. And there's our Newman projection, minus the two H's at the right. The bottom right here, it should just be one H, it's not two. CH3, yep, just like that. So there we've constructed a complete Newman projection for the entire molecule, but is it the lowest energy state possible? Well, looking at it right here, we actually see that we have the chloral group and the methyl group really close to each other. And that can create a lot of steric hindrance. So actually the molecule is going to want to rotate away from that in order to make that interaction less protruding. So how do you think we should rotate this molecule so we can get the carbon group up here the methyl group and the chloral group furthest away from each other as possible. So it would make sense to take this methyl group over here and rotate it over there. So it's next to the methyl group, or I mean the isopropyl group. Just double bond, just single bond, please. So there's our methyl group that we've rotated over. Then we'll put our 2 hydrogens in. And there you see is one of our lower energy states possible. Now you can see it still puts the 2 methyl, it still puts those 2 carbon groups closer together, but we have moved away further from the chlorine. The chlorine has more density than either of these 2 groups combined. So with that in mind, that's one of the 3 lowest energy conformations. Yeah?
So on the left, like when you do that, how did you get the
The HC.
at the very top?
Oh, yeah. So see down here, it's CH, CH3, CH3. It's this methyl group, or it's this whole thing right here. We've got a CH in the middle, 2 CH3s on the end. That's the, so see right up here, we've got this kind of fishtail structure poking up the top. That's exactly what it is over here as well. In the Newman projections, we have to show everything that's attached to the molecule. Sure.
Alright, so I'm just gonna put the lights on.
Do you want to do it on here?
Here, let's do it on the board.
That's fine.
Alright, so whenever we look at molecules, like you said, you'll want to try and identify, like he'll give you a specific bond to look down. Yeah. Oh, you mean the section methyl, the isopropyl group? Yeah. You're just representing that this right here is this connected to this carbon. So you're saying you have to draw everything like all the lines and not saying. Yeah, I mean you could write the molecular formula, just it's long-handed at that point. Yeah. But you can abbreviate it as long as there's nothing else attached to it that's causing the thing through. That's a good question. So we didn't draw all of them, but we will draw all of them on this one, alright? So let's name this molecule really, really quick. The highest part of the functional group is the hydroxy group right here. And we count the carbon chain 1, 2, 3, 4, 5, so it's a pent. And then ane molecule, right? We'll just label 1, 2, 3, 4, 5. And we want to try and put everything as the highest part of the functional group and the lowest number. So it makes sense that it's at the 2 position right here. And so let's quick name this. We have also here a 3-methyl and a 4-methyl right here. Alright. Does anybody have the name before I write it out? It's okay. Early, I know. So we would have a 3, 4 dimethyl. And then pent. And 2-ol. Alright? And like you said, the names, we might not do all the names with you guys just so we can practice the Newman projection. But it's important to be able to know how to name a molecule so that you can find the bond that they specifically So like you might say look down to C3 and C4. So now I know that my C3 and C4 are this right here. Does that make sense? Yeah. So now my eye is going to be right here, and then look up to the molecule.
Yeah, that's right.
That's right, right? Yeah. So when you're drawing in a projection, you start with your circle, and you look right here, and what I like to think is that whatever I see going down is immediately down, alright? So I see this methyl group going down, and then I see this isopropyl coming off, and then I have a hydrogen in here as well. So my isopropyl group, and then I have my hydrogen. It doesn't matter which one will go left or right, as long as you keep it consistent with the next one that you draw.
Wouldn't the isopropyl group be in the back?
In the back.
It's like,
Oh, I see what you mean. Yeah. You're right. So there's the hydrogen. Yeah, that's the back carbon. Yep, sorry. Thank you. Yeah, so this back group though, the methyl is straight up right here, CH3. Right.
We need the
So you have
alcohol group.
alcohol in the group. I think it's not. I think it's C1, 2, 3, 4, 3, 3, 3. This one, you have to look on the other bond. I think you have to look on this bond. I'm sorry, guys. It's my bad. To be able to draw accurately, you have to look on this bond. Done this way.
No, it's the other way. 3 to 4. Yeah. It's just you've got your hydrogen and you've got your methyl group.
Oh, here's the oxygen. CH.
Yeah, so it's like that.
And then OH.
Yeah, you're just getting confused with how to draw the OH on there.
Yeah, so that's how you would like kind of draw bigger groups. Someone asked that before, yeah. So like this group is really, really big, right? It's you want to get as far away as possible with something else. Sorry, Jim.
Why don't we do like the two bars
The 2 bar
of
that one. You could really draw it as if you see it that way. So it could have been drawn like OH, CH2. Does that make sense? OH, CH2. You could draw that way. Alright, and so then we have our methyl group in the back, another methyl group right here, and then our hydrogen group.
Can you go step by step with that?
Yeah. Like, what's like how you go down?
How did you come up with that?
So when you name the molecule, you did 1, 2, 3, 4. It said look down the 3, 4 bond, right? And so when I'm looking at the 3 bond, I see a methyl group coming straight down, and I always draw my first group in the very front. Then I also see a hydrogen attached to it, and then to this group as well is this huge chain. Okay. Does that make sense?
Yeah.
There's like 3 chains. Then when I go to this back carbon, I have a methyl group, and a hydrogen. Methyl group, hydrogen. Does that make sense? So if I was to draw the next or the next confirmation of it, I would leave one group the same. Don't change both, otherwise we'll get confused. So I'm going to leave the very front the same. Alright, so leave the front the same. Yes.
I was curious, it looks like there's 6 carbons like in the chain, but they only have 5 on your drawing. So I don't know.
1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
But like on the like methyl group too.
So since the C
So there are 7 total carbons, is what you're wondering, right?
Or 6. And then we only have 5 on.
1, 2, 3, 4,
That's because
5,
the
6.
center where the
is-
lines,
okay.
center and the circle are implied as carbons.
So what I like to think when I'm drawing Newman projections, you guys, so once you have to rotate the back one, and I kind of think of it as like, if I was in my recitation yesterday, you know those like old school locks that can like flip in place, like when you turn it just the right way, kind of idea? So that's what's happening here. So I'm going to turn this group one click to the right. And so the CH3 group will come down, this CH3 will come up, and this group will come over. So click down, click down, click down. So it's just rotate it. And then you can see which ones are the more like stable based on like where they're at. So like right here you have a lot of steric hindrance, so here are a lot of steric hindrance, a lot here, a lot here. Those two are pretty much equivalent as in like not being very stable. So you'd want to draw the third one to make sure you have the right projection. Small for it, sorry. So you see that again, they're all pretty much equivalent. At that point, you just circle that they're all equivalent. They all have two steric hindrances. There's not really one that's more stable, but there usually is one in the molecule. So like for some reason.
And this one not so much because everything has a steric group attached to it.
Yeah. So does that make sense how you rotate it, you guys? That's how you can find what's the most stable. Yeah. Yeah, so when you have a line that just comes straight down, you can assume it's C. You don't have to label it. Good question.
So you didn't have to label the other CH3.
Nope, I didn't have to, I just did. Okay. It has one in here too. Sorry. Yeah. So they all have three. If you had to pick one, probably the one that's most stable. Wherever the big bulk groups are furthest away from each other. So it'd probably be this one. Alright.
So why like on this one is the steric between the CH3 whenever you're on the right and the top left?
Oh, sorry. That's just sorry. So technically, yeah, there isn't one right here. There is one right here, and there is one right here. Because the CH3 group, CH3, and these big groups that are in a big chain next to that creates hindrance. Yeah, they're like, hey, this would not create a hindrance.
That's your question? Usually it's possible to go from C4 to C3, but it's usually lower number to higher number. I don't think he would say look down like 6 to 5. Yeah.
So on the C3 what is it an ethyl group that is
C3 carbon. Right here is a methyl
I mean
group.
the C4.
The C4
Yeah, and where is it from the moving projection?
right here.
Oh. So
the
the
C4 right there. And this methyl group is right here. Then there's a hydrogen.
the two carbons we're looking down we don't include. Well, we do include. It's just it's the intersection in the middle is the front carbon, and the circle in the back is the other carbon. So now looking at this one's actually pretty easy to name as well. It's just going to be, we have a pentane group, so it's just going to be 3-bromo, pentane. And so again, we're looking down carbon 3 and carbon 4, but you might think, wait, but I can number it either way, 1, 2, 3, 4, 5, or the other direction, 1, 2, 3, 4, 5. They're exactly the same. So it really doesn't matter what you choose as your 3, 4 position, as long as you're just consistent with yourself. So I'm just going to do it like this. I'll call this carbon 3. I'll call that carbon 4. I will just... Now I'll just erase the name for a second. So with this carbon in the front, let's add our hydrogens. So this is how I like to see it. So the hydrogen is coming out in the back of the page, right? And we know that the bromine, we can draw it like this with a solid wedge line, is just coming out in the other direction. And then what's coming out the top is just this ethyl group right there. Did everyone see that? What's that? Yeah, you can just draw it like that. You mean like this? It doesn't matter. It really doesn't matter. And then for carbon 4, let me erase the 4 so I have room to write. So again, we've got our two hydrogens both coming out of the page. Those are just simply opposite of each other. So I'll just draw those right here, H and H. And then what do we have coming down here? CH3, correct. So this one is definitely not one of the, well, it could be. We've got some sterics between this bromine and this methyl group. Bromine is a very heavy molecule. It's 35 on the periodic table. So we're going to want to rotate that in order to get rid of that steric hindrance occurring between those two. So I'll rotate the back. So I'll rotate it 60 degrees. So all you have to do, so we'll redraw the front. And everything literally just switches places. So we've got the methyl group over here. Got the hydrogen, oh sorry, these should be more joined in the middle. Methyl, hydrogen, and hydrogen. So this one still has some steric hindrance between these two alkyl groups, the methyl and the ethyl group, but that's still going to be less than with the bromine because the three carbons do not have as much density as does the bromine by itself. Yes? So steric hindrance. So sterics, remember, so sterics is simply electron repulsion. So we're looking for the groups with the most electron density associated with them. So bromine, its place on the periodic table, its atomic number is 35. And so it has 35 electrons associated with that to balance out the charge. The methyl group, the carbon and the three hydrogens, it's got 6 electrons and then 3 electrons for the hydrogen, so that's 8 electrons for that group. And then for the two carbons in the ethyl group, I'm just going to call that 12. And there's still, I didn't include the hydrogens in there, but well, let's just include them in there. We've got 5 hydrogens in there. 12 plus 5 is 17. So the higher the number, the more steric hindrance it causes.
So it doesn't cause steric hindrance when there are like two atoms of the same kind?
2 out of the same kind. So 2 carbons, so any electron will repel any other electron. It's just comparing this. So you understand that the bromine has more electron density as a whole than either of these two other groups right here. This methyl group is still going to cause some steric hindrance with the ethyl group, but it's going to be less because it's less electron dense over here than it was when it was next to the bromine. Does that make sense? All right. I think we've done that problem pretty well. Yes?
So it doesn't matter where we put in the rotation as long as we're consistent with what we put on the back carbon.
Basically, yeah.
You guys are going to these quizzes, you're going to see a bunch of different intersections.
Yeah.
No one perfect one like this. Making sure
It's wherever you started, make sure you keep that same order once you rotate it. Does that make sense? Yeah, so that comes to understanding, just like we talked about yesterday, how certain groups take up a lot of space. And certain molecules have maybe electrons around them, right? It's like a bromine group would have
Whoops.
a lot of electrons around it, creating a lot of density right there. And then a CH3 group is just really big. Notice how much space it takes up. So if those groups are next to one another, they'll create hindrance. Does that make sense? And so when you have molecules that are bigger on the outside that you're attached to, you have to consider in your Brownian projections what's going to be the most stable. And the most stable is the one that has the least steric hindrance in there. Does that make sense?
Everything you draw is going to have some form of steric hindrance. It's just a matter of minimizing that as much as possible.
Okay.
We should probably skip the last
Yeah,
three.
so we're going to knock through the last three. Just with the time, we do want to go over double bond equivalents so that you know how to do this. But if you have questions about neural projections, we can happy to help. I will be in the county lab from 9 until 10 this morning. So, yeah, so I can hop in too. Alright, so, double bond, huh?
I can do this one.
Okay, sure.
So when we're doing double bond equivalent, remember that the E is very important right here. It means it could be a double bond or something else that takes the place of a double bond. Because when we're talking about double bond equivalent, we really mean we lose 2 hydrogens. And that's exactly what a double bond does for us. Because if we take butene, we can just take this molecule down here. Thank you, Mariana. So if we compare this with the alkane, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. Versus here we have 1, 2, 3, 4, 5, 6, 7, 8. This has 8 hydrogens. This has 10 hydrogens. The double bond eliminated 2 hydrogens. Same with the ring we experience up here. If we did a cyclobutane ring, we'd have 1, 2, 3, 4, 5, 6, 7, 8. So both rings and double bonds cause us to lose 2 hydrogens. So we can calculate the double bond equivalent either by just looking at the structural formula, which we have right here, or we could calculate it given the molecular formula. So let's do it both ways, just to see how it works. So this one we see we have double bond, and a ring. 1 plus 1 plus 1. We should have a double bond equivalent of 3. And doing that the molecular formula way, let's just count everything we have. We've got 6 carbons right there. 1, 2, 3, 4, 5, 6. We've got 1, 2, 1, 2, 1, 2, 3, 4, 5, 6, 7 hydrogens, 1 oxygen, and 1 chlorine. So in the normal alkane, we'd expect 6 times 2 plus 2, 14 hydrogens total, but we've only got 7. So somehow the shape of this ring has to be contributing us to losing 7 hydrogens. So looking at the oxygen actually does not change if you look at the sheet, it does not change the number of hydrogens we have in the molecule overall. The chlorine, however, does actually cause us to lose 1. So we take 14 hydrogens, we subtract 1 hydrogen for the 1 chlorine we experience, and we have to subtract out, this is very important, the original 7 hydrogens that we experience in the formula. So that becomes 14 minus 8, which is 6 hydrogens, and 1 DBE per every 2 hydrogens, so 6 divided by 2 is, voila, we've got 3 double bond equivalents. So if you're given the structure, it's easy just to count the number of double bonds and the ring, and then you get it from there. If you're given the molecular formula, work through it like I have shown here. You want to keep going? Do you want to do the constitutional isomer one?
Sure.
So as far as the constitutional isomer goes, that basically means it's got the same molecular formula, but different arrangement in space. So to draw a constitutional isomer, we could literally just take this chlorine group and move it on over right there. So I'll just draw it down here for simplicity's sake. We just have the chlorine, got the the carbonyl, got the double bond, and move the chlorine right there. We've got a constitutional isomer. A good way to tell if you have a different constitutional isomer is to name the molecule. If you come up with two different names, you have two different molecules. Therefore, you have two different constitutional isomers of each other. So this part right here, draw a constitutional isomer, is really not that bad.
Yeah, constitutional isomer is literally the same chemical formula, just a different drawn molecule. Yeah, no, you could draw it like a long chain. You just have to be very careful how you do it. Yeah, I mean that's just one way to do it. That's one way I could use that chemical formula. But you could have two double bonds in your alkene, or two double bonds in like the actual C dual bond. They're the same. Yeah. Any other questions on it? Yeah.
Here, I can do that. I can do that really quick.
Huh?
I can do that really quick.
Sure.
So here you see we're given the molecular formula, so we have to do it the way we have up here. So let's calculate the number of expected hydrogens let's calculate the number of hydrogens we would expect, not the expected. That's a bad thing. So we have 6 carbons right here. So in the alkane, it would be 6 times 2 plus 2. We would expect to see 14 hydrogens. However, we only see 10. So again, we look at these other molecules and see what happened to contribute to such. So 14 hydrogens, the oxygen doesn't contribute any, or doesn't add or take away, but the 2 chlorine groups actually take away 2 hydrogens, 1 for each hydrogen. And don't forget, again, we have to subtract out the original number of hydrogen atoms. So 14 minus 2 minus 10 hydrogens originally. 14 minus 12 is 2 hydrogens. So that is equivalent to 1 double bond equivalent. So in this formula, we'd expect to see either a ring or a double bond. Ring's probably the easier one to do. And for this one, it doesn't have to be like the right molecule. It just has to make sense based on the double bond equivalent that you've calculated and everything coming off of it. So right here, you could see with the cyclohexane ring, that would get us up to 12 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But we've got to add the oxygens and the chlorine somehow. So we could simply just add a chlorine here, chlorine there, and then an OH. And then counting the hydrogens, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there is a valid constitutional isomer of the structural formula.
I think there is a class in here afterwards, so we'll have to get going. But thank you for coming. You're going to do good.